Assalamualaikum. Today we will be presenting a product titled Smart the Doorknob. This is my group name. My name is Muhammad Amirul Syahmi bin Muhammad Basri. I'm the first presenter. And this is our topic. First topic, product chosen. The main product we have chosen is the doorknob, where the primary issue often faced is security. Traditional doorknobs have several weaknesses, such as lost or stolen keys, which can result in someone being unable to access their home or worse, allow unauthorized individuals to gain entry. Additionally, traditional doorknobs are vulnerable to force entry techniques like picking and bumping. To address both of these problems, we propose upgrading to doorknobs with fingerprint technology, which only allows register fingerprints user to open the door. The significantly exchange security by reducing the risk of lost or stolen keys and preventing picking and bumping techniques. In conclusion, switching to fingerprint technology will extend home security and provide peace of mind for users. A well-designed door not only serve its practical purpose but also add a touch of elegance to any rooms. Moreover, it is important that the doorknobs are affordable and of high quality as consumer want to products that are both cost-effective and reliable. This blend of functionality, security, style, and affordability make the doorknob an indispensable element in our homes, office, and public buildings.
As ergonomic door opening devices, doorknobs provide users with a simple way to enter and exit by enabling a grab and turn action that requires little physical effort, thereby guaranteeing accessibility for everyone. By adding locking mechanics, they improve the security of enclosed areas and provide residents with a feeling of privacy and protection in a variety of architectural contexts. There are three types of doorknobs comparison with existing products on the market, which had its own set of advantages and disadvantages. The user places a high value on the first product criterion, which is the product safety aspects. These safety aspects collectively enhance home security by offering convenience, control, and real-time monitoring capabilities, making smart doorknobs a reliable choice for modern homeowners. Product 3 was less secure than others since it doesn't have key slots or holes. For the material for our product, it is crucial to pick the best material for indoor and outdoor knob. We changed the size and material for our latest designs. We are using brass. Brass is known to be the best one since it can provide resilience towards rust but at the same time can keep the premium aesthetics compared to others. We also made the battery portable and swappable with another battery on standby so it can be used continuously. There are three design concepts for our product. The first design has been improved with our innovation using power sources from battery to power up the thumbprint system on top, but a bit bulkier because we also put keyhole for the design. For the second design, the product itself been upgraded to be a lever type knob for it uses only a twist lock. For the third design, we improved the design by making the battery swappable and the thumbprint is in front of the knob. As for that, this is the best design for our product.
Assalamualaikum and hi, my name is Nur Aidi Hafizin. Today I will talk about a reverse engineering process and the complexity of the features used in CATIA to reproduce the product. Reverse engineering process allow us to determine how many part was designed from the parts so we can recreate it. First, we bought a home doorknob to be a sample. To get every part of the doorknob, we disassemble the doorknob. The purpose of disassemble is to get every detail inside the doorknob, such as part system, how it works, and also measurements such as length and weight. After disassemble, we use a vernier caliper to measure dimension for every part from the doorknob. The purpose of the redimensioning is to roughly redraw a product to redesign it in computer software such as CATIA.
So I'm going to talk about features involved in our project. There are many features that we use, but I'm going to cover 6 features that we commonly use. So the first one is line, polyline, padding, shell, hole, and circle. So for line are basic essential elements that use extensively in the Sketcher workbench to create profile for more complex geometries. Polyline, while polyline is to create a series of connected line within a single command. Now for padding is to create a 3D solid by extruding a 2D sketch from the Sketcher workbench. And for shell is to create a hollow thin wall version of a solid model by removing material from its interior. And then hole, which basically create a hole, and then a circle, which is mainly used in our project, in our CATIA, which are defining round features like holes, bosses, and other cylindrical shapes. That's all from me.
In this mini project, we use a CATIA to reassemble the part. So next, after we redesign every single part of the doorknob, we reassemble it to reproduce an actual product in CATIA. To assemble a parts in CATIA, we use an advanced features called Assemble Product. There are 3 main features used to assemble a part. Firstly, coincident constraint, which allow user to constrain two selected point to remain attached. This feature will align the object to the whole of product such as a screw or clip. Second is contact constraint. This feature allows user to attach any part surface to the product surface. Usually, after we use a coincident constraint, it will follow up by contact constraint. This feature will ask user which surface will be attached. Select two surface and click update and it will attach based from selected surface. Lastly, we use an offset constraint. This feature allows us to create an element offset from the reference line, plane or surface. When defining an offset constraint between two components, you need to specify how face should be oriented.
Hi, Assalamualaikum. My name is Intan Shafika binti Ismail, and now I'm going to continue the presentation with finite element analysis. It has 2 parts, which is lash and spindle. Finite element analysis is a tool in computer-aided design or modeling software that generates quantitative analysis for testing and assessing buildings and components in theoretical settings. The latch in a doorknob is a crucial component that helps to secure a door. When the doorknob is not twisted, the latch engages with the strike plate in the door frame to keep the door closed. The assumptions made, as well as the loads and supports applied to the latch, are outlined. With all the required data gathered, finite element analysis or FEA can be conducted. For assumption, the latch is made of brass. This table shows the properties of brass material used for the latch. As you can see, it has Young's modulus, Poisson's ratio, shear modulus, and density. Load and support applied. In this case, we used a distributed load of 100 Newton shear force applied tangentially to the latch. The base of the latch is fixed. Based on the second figure, it is possible to see the von Mises stress result for the latch following computation. The second figure reveals that the latch maximum von Mises stress is 8.94 MPa, which is also its maximum allowed stress. We can also observe that the shear stress for this portion is 41 GPa as previously mentioned in table of properties. As a result, the factor of safety, FOS, can be easily calculated by dividing the shear stress value by the maximum stress, giving us the FOS value of 4.59. For displacement, the lash maximum displacement value is 6.09 mm, which may affect the operation of the lash. If the lash no longer aligns correctly with the strike plate or door frame, it could hinder the door's ability to open or close properly. Now I'm going to explain part 2, which is spindle. Finite element analysis (FEA) on a spindle in a doorknob involves evaluating the structural performance of the spindle under various loading conditions. The spindle is a crucial component that joins the doorknobs on opposite sides of a door and transmits the rotating force required to activate the latch mechanism. The assumptions established, as well as the loads and supports used on the latch. With all of the necessary data acquired, finite element analysis may be performed. For assumption, table below display the properties of the spindle, which is also made of brass. It has Young's modulus, Poisson's ratio, and also yield strength. For load and support applied, we apply a torque of 5 Nm to the tip of the spindle. As you can see on the second figure, the spindle's maximum Bohr meter stress is 6.92 MPa. We also can see that, as previously stated in table of properties, the yield strength for this component is 250 MPa. By dividing the yield strength value by the maximum Bohr meter stress, we can simply compute the factor of safety, FOS, which yields the FOS value of 36.13. For displacement, based on the preceding research, the spindle's maximum displacement value of 11.8 mm could severely affect the spindle's ability to transmit the rotational force needed to operate the latch mechanism. This may result in malfunctioning of the doorknob.